Hello, everybody. This is lesson 3.6, derivatives of logarithmic functions. At the top of our notes here, we have some rules to go over. The first rule you need to know is how to take a derivative of ln x. So the derivative of ln x is 1 over x. And just a reminder here, I'm going to write it on the screen, that ln x is actually a log function, so log base e of x is the same as ln x. We just use it so commonly, it's just a common base to use that we've given it its own name, and typically on your calculator you'll have a button for ln as well. On the right-hand side are not calculus rules, they're rules from pre-calculus involving logarithmic expressions. So just kind of review those. You should have learned these in your pre-calculus class, and we're going to be using them today. Okay, so let's start out with a simple example where we just have ln of x squared minus 5, and how do we take the derivative of that? This we would use the chain rule, since we have a function inside another function. So my inner function is x squared minus 5, and my outer function is ln. And so I'm going to take the derivative of the outer function first. So f prime x equals. So the derivative of the outer function, if it was just ln x, it would be 1 over x. But here we keep the inside there. So where the x would normally be, we're going to put that inner function, x squared minus 5. So that's the derivative of the outer part. Now I need the derivative of the inner part, that yellow part there. So the derivative of x squared is 2x. And the derivative of negative 5 is 0. We can write this a little bit nicer, just combine it into one fraction. There we go. So the derivative of ln of x squared minus 5 is 2x over x squared minus 5. Okay, let's try one where we have the product rule. Now, in this question, when you're doing the derivative of ln functions, the first thing to ask yourself is, can I use a log law, something you've learned in pre-calculus 12, to simplify it and make it easier to take the derivative. You're going to want to do that, especially when the functions get quite complicated. There's a lot of ways you can simplify them, so the derivatives become a lot easier. Okay, so can I use a log law to simplify? In this case, we definitely can. Whenever you have an exponent inside a log expression, we can bring that down in front. So before, I'm not taking the derivative yet. I'm just making this simpler. I'm going to bring that 3 down in front, and I'll put it in front of the sign x, just because that's where typically we write our constants. And then it's just ln x here. Okay, so now I'm taking the derivative of 3 sine x times ln x. And now I don't have to do the chain rule anymore. I just have a product here. So I'm going to use the product law, the product rule, sorry. And so the derivative of 3 sine x would be 3 cos x. Leave the second function. That's not a subtraction, that's a multiplication. And then I'm going to add and take the derivative of the second one. Now the derivative of ln x is 1 over x. You can write this a little bit nicer. 3 cos x ln x plus 3 sine x over x. There we go. So you definitely want to do this simplification here before you start any question where you're taking the derivative of the log function. We'll see that in the next example, especially. We're going to really simplify that down first. Okay, so let's try the second one, or the third one, sorry. Okay, this looks quite complicated. We have ln, and then inside the ln function, we've got easy x over x plus 1 cubed. Now, normally, if we didn't simplify this at all, you'd have to use the chain rule, and then within that chain rule, you'd have to do quotient rule. So it would be quite a lot of rules to kind of combine, but if we are paying attention and we use our log laws to simplify first, everything becomes so much easier. So one of the log laws, I'm just going to scroll back up to them. So we have a division going on, or a quotient inside our ln function, and there is a law for that. We're going to use law number 3, which says if I have a quotient inside my ln function, I can separate it into 2 separate lns with a subtraction sign. So I'm going to do that first. Oops. So remember, I'm not taking the derivative yet. I'm just simplifying this expression. So it would be ln of e to the x minus ln of x plus 1 cubed. Now I can simplify this even further because any exponent can be brought down in front. So I'm going to do that now. So it'll be x ln e minus 3 ln x plus 1. Now, finally, I can make this even simpler because ln of e is actually just 1. Remember, the base for the ln function is e as well. So ln e evaluates to 1. So this would just be x minus 3 ln x plus 1. Look how much simpler that looks compared to the first. So that's the function now that I'm going to take the derivative of, x minus 3 ln x plus 1. I don't have to do quotient law anymore. And I have a small chain rule to do, but it's not so bad. Okay, so now let's take the derivative. So the derivative of x is just 1. The 3 is a constant, so we can ignore it. And when I take the derivative of ln x plus 1, it is a chain rule. So I'm going to do the outside first, and then the inside. That would be 1 over x plus 1. That's the outer function. And then times the derivative of the inner function, which in this case is actually just 1. So I'm going to write this a little bit nicer for my final answer. 1 minus 3 over x plus 1. Look how simple that derivative looks compared to like what we started with at the beginning. So that's why it's really important you use those log laws to simplify your answers first. Okay, so all 3 of these questions here, we were taking the derivative of functions that involved a ln. In the next examples on the back, it's a different type of question because they're not going to actually involve, the original function is not going to have any lns or logs in it, but we are going to use them to our advantage because we're going to be dealing with quite complicated looking functions. I still have the rules again here at the top. These haven't changed. They're the same as the ones on the previous page, just for you to refer to as you go. Okay, so let's have a look at this first one here. Excuse me. Y equals x to the power of root x. We actually don't have a rule for this when we have an x in the exponent like that, especially when x is a base as well. So we don't have a way to evaluate this with what we know so far. So we're going to do something called logarithmic differentiation here. And there's a few steps to this. So the first step is always, so I'll write the steps on the right-hand side as I go. The first step is always take ln of both sides. In math, when you're working with equations, as long as you do the same operation to both sides of an equal sign, you're not actually changing the equation at all. So this is a legal move that we can do, and it's going to help us out, and we'll see how that helps us out in a second. So I'm going to apply the ln to both sides of the equation. Okay. Now, once you're here, we can take advantage of some of those log laws to simplify this down a little bit. So use log laws, spelled it wrong, to simplify, just like we did on the first page. So here we have an exponent inside a ln, which means I can bring that down in front. So we have ln of y equals root x times ln of x. Okay, I don't think I can simplify that anymore. So now I'm ready to take a derivative. So up until this dotted line, we haven't done any calculus yet. Now we're going to start doing some calculus and take the derivative, because that's my ultimate goal here, is to find the derivative of this function. Okay, so now I'm going to take the derivative of both sides. Take derivative with respect to, that's what WRT stands for, with respect to x on both sides. This is an implicit equation here because I don't have y equals on one side. So we need to use implicit differentiation that you learned in 3.5 to do this. Okay, This kind of is a review of 3.5 for you. Okay, so on the left, the derivative of the outer function, which would be ln, would be 1 over y. And then I need the derivative of the inner function. So the derivative of y, we don't know what that is, so we just write y prime. Or you can write dy dx if you like. Okay, let's do the right-hand side. This is a product, so we need product rule. The derivative of root x would be, so that's a x to the 1/2, so we bring the 1/2 down, reduce the power by 1, leave the other function, and then we're going to leave the 1/2 and take the derivative of ln x, which would be 1 over x. Okay, now we're ready to simplify this down, and we are going to solve for, our ultimate goal is to find what y prime is. So we're going to solve for y prime in a second too. But first, we'll just simplify this down and make it look a little bit nicer. So the first one looks like this, ln x over 2 root x, because x to the 1/2 can go to the denominator. And this one over here, if you subtract the exponents, this has an exponent of 1, you get x to the -1/2. So it would be 1 over root x. Okay. You could also leave them as 1/2, that's fine. Either way is okay. And we still have this 1 over y hanging out here. Okay, so now we need to solve for this y prime. So what we're going to do to both, as long as you do it to both sides, it's fine. Multiply both sides by y. The reason we want to do that is because it eliminates it from that left-hand side, and we're just left with what we were interested in from the beginning, which is y prime. Now, we don't want y in our final answer, so we do know that y equals x to the power of root x, so we'll write that instead of y. They're equal to each other. That way our final answer will just have x's in it. So ln x over 2 root x plus 1 over root x times x to the power of root x. That is quite a complicated looking derivative, and we would have never got there unless we used logarithmic differentiation to help us simplify it with those log laws. So let me go over the steps again. They're always the same steps when you're doing this type of differentiation, and we'll use the same steps again in the next example. So first you take ln of both sides. As long as you do it to both sides, you're not changing the equation. Then you use log laws to simplify. We haven't done any calculus up until that dotted line. We've just used log laws. Then we take the derivative of both sides and then solve for y prime. Okay, let's try it again. If you're feeling pretty confident, you could pause the video here and try this on your own and then just come back to check your answer if you like, or you could do it with me. Okay, so let's do step 1, take ln of both sides. Ln of y equals ln of this big, ugly looking function here. This one you actually could take the derivative without logarithmic differentiation, but it would be a nasty product and quotient rule, really take a long time to do it. So logarithmic differentiation really helps break it down and simplify it. Okay, so now we're going to break this apart using the log laws. We have a product and a quotient, so we can separate it out. So remember, we're not doing any derivatives yet. So when you have a product, you can add them, the ln of root x plus 1. And then when you have a quotient, you could subtract. So it would be 3x plus 2 to the power of 5. Okay, I have some exponents in all three, so I'm going to bring those down in front. Again, I'm not doing any calculus yet. I'm just using log laws of x ln e plus the square root is equivalent to a power of half, so I'll bring the half down in front. And then 5 ln. This already looks a lot simpler. Okay. See, the advantage of log laws is it turns things that you would need to use product or quotient law with into like separate functions that are added or subtracted, which is easier to differentiate. Okay, and then the last thing here is I'm going to erase this ln e because ln e is just 1. So it's just x. Okay, now I'm ready to take the derivative of both sides. So on the left side, remember, we're using implicit differentiation. We're taking the derivative with respect to x. So this is technically a chain rule that I need to do. So the derivative of ln is 1 over y, and then I need the derivative of y. So I'll just write y prime. Derivative of x is 1. Here we have a constant in front, so we'll ignore that for now. And then the derivative of ln of x plus 1, we've done that one before, would just be 1 over x plus 1 times 1. The derivative of the inner function there is just 1. Then here we have 5, which we can just ignore, it's a constant. And then again, another chain rule. So 1 over 3x plus 2, that's the outer function. And then the derivative of the inner function would be 3. Let's write this a little bit nicer, and then we'll solve for y prime. So we'd have this one on the numerator, we'll just have a 1, and then we have 2 times x plus 1 in the denominator. And here in the numerator, we have 15 and 3x plus 2 in the denominator. Okay, now we're ready to multiply both sides by y. And remember, we don't want y in our final answer. That cancels out the y on this side. So I'm just left with y prime. We don't want y in our final answer, so instead of y, we will write the original function that equals y. I'm going to scroll up and find that in a second. So instead of y, it was e to the x root 1 over x, or 1 plus x, all over the 3x plus 2 to the power 5. Look how complicated that looks, but it was a lot easier than doing like a product and quotient and chain rule. You would have had to use all 3 of those rules, and it would have been pretty nasty if you tried to do it without logarithmic differentiation. So there you go. And that is the end of the lesson.